Hey AP Physics 1, this is Horner, and this is the easier of the two 2008 problems. This Form B question would be a great test question. The other 2008 problem I think is a little goofy, but wanted to go through it anyway just so you could kind of see what it was like. So here I've got a 4,700 kilogram truck carrying a 900 kilogram crate. So these two have different masses, so we're going to need to think about that. It's traveling at 25 meters per second to the right along a straight level highway. The truck driver applies the brakes and it slows down. And as it slows down, it travels 55 meters in the next 3 seconds. It does not slide on the back of the truck, so it just sits there still. So we know that there's got to be some friction and some things going on. They want us to just find the acceleration of the truck, assuming it is constant. So we're going to express our terms and express our answer in terms of xf, xo, vo, and we'll have to use t. So obviously this one we do have all of these terms. So let's think about an equation as xf, xo, vo, and t. Notice the only thing that we don't have here is final velocity. So if that's correct, let's try the equation without final velocity. It's xf is equal to xo, or the change in position is equal to VOT, and then this is going to be minus 1/2 AT squared, because we know that it is slowing down. At this point, we need to find our expression, and our expression is just going to be, we need to get everything on this side, so we're going to say XF minus XO, and we're going to put that in brackets, and it'll be, then we also need to do minus VOT. So now we're going to divide both sides, and we're going to divide both sides by t squared and multiply both sides by 2. So I need to put a 2 here, and that's equal to a. The only other thing that we have is we forgot our negative, which is still here, so we're going to put the negative out there too. So that is our expression. I'm assuming that on this they'd probably give you 1 or 2 points, probably 1 here, and most likely 1 for the actual expression itself. The next thing they want us to do in the problem is calculate the magnitude of the acceleration of the truck. So we'll just go ahead and use our equation that we started with, and we'll just kind of move through it. So this is equal to negative 2, and then so our final position here is 55 meters. Original position is 0, so I won't worry about it. And then we're going to subtract from that. Here, let's put these in brackets so since this is really times the whole thing. We need to subtract from that the original velocity, which was 25, times the time, which is 3 seconds. And now that we've done that, we need to divide by the time squared, which would be 3 squared. If you do all your math, you should get a value for A, and that value should be negative 4.4 meters per second squared. Assuming you probably get 2 points for this, 1 for plugging everything in correctly, 1 for the answer. It has to have a negative and has to have the units, or you wouldn't get that point. So if you had just 4.4, no points. 4.4 meters per second squared, no points. But if you had negative 4.4 meters per second squared, you should get all the points on that. Cool. Let's go on to the next part. Next part says, in the diagram below, draw and label all the forces acting on the crate during braking. So I know that the force straight down has got to be the mass of the crate times gravity. Force up is the normal force coming from the truck bed pushing up on that crate. There's no force to the right. It's moving to the right, but there's nothing pushing it to the right. However, there is the force of friction pointing to the left, and that keeps it from flying towards the cab of the truck. Next thing that they want us to do on this is it says derive an expression or an equation for the minimum coefficient of friction between the crate and the truck that prevents the crate from sliding. So we're looking for static friction here. So let's go ahead and make our equation. I'm going to move this down and go back, draw our free body diagram. So that was the normal force going straight down here was mg, and then to the left was the force of friction. So here we go. Sum of the forces should be equal to mass times acceleration. The force that we have that is going to the left here is the force of friction. We don't really have anything going to the right. And we also know that it is accelerating. Remember, it's accelerating in this direction. So it's accelerating to the left. So let's go ahead, and I know that everything is going to the right, so we'll make that positive. So this is going to be negative FF is equal to M times negative A. But notice the negatives go away, and we're just left with FF is equal to MA. Remember our force of friction, just as a side note here, is equal to mu times the normal force. So we're going to substitute that in here. So this is mu times the normal force, and that's equal to M times A. And because going up and down, the sum of the forces going up and down or in the y direction are equal to 0, we can say the normal force minus mg is equal to 0. So the normal force is equal to mg. So we're going to take this and we're going to plug it in over here in the normal force. So let's go back and do that. So now we have mu, oops, wrong color. Mu is times mg is equal to ma. The m's will cross off, and so our expression for u is equal to a over g, and that would be our final answer. So several points here, probably a point for this one. You would get a point for substituting in. You'd have to have a point for making this more distinct, so just force of friction won't work. You've got to have mu times Fn. Then I would say a point here, a point here. Substituting in will give you a point, and then getting your final answer. So this is 1, 2, 3, 4, 5, 6, 7. In the free body diagram, you're probably going to get 3. 1, 2, 3. Next thing that they want us to do is use our equation and actually come up with a value. And so remember our equation again was just mu is equal to a over g. Our acceleration we determined earlier was 4.4. I know it's negative, but we don't usually have negative values here. So we're going to make it positive 4.4, and we're going to divide it by gravity. Let's use 9.8, and we end up with 0.45. And notice there's no units because this is meters per second squared, and this is also meters per second squared. And so we are left with our answer. 2 points for this, 1 here, and 1 for the correct answer with the right units. The next part of this problem states you've got a student asked if their friction is static or kinetic, and oops, the student reasons, so let's move back up here. The student reasons that the friction must be static because it allows the box to move across the bed of the truck. What is correct about the student's reasoning? Static friction is correct. And it's because the box stays on the bed without moving. Now that's without moving relative to the bed, so we can say no sliding. What is incorrect, and it is their explanation, and it says the box moves across the bed. So the box does not move across the bed. They want to know why, and it's basically because that's what the problem reads. Problem directions. And that's probably all you would need to say. Here, 2 points for each one of these. 1 for your statement, so let's go ahead and do this. 1 for your statement, 1 for your explanation. This one's goofy. 1 for your statement, 1 for your explanation. Probably the other thing you could put here, problem directions, or you could say that if sliding, then the force of friction is kinetic. and that would probably be the better answer for that one. That was part F, and yes, there is more to this one. So let's go on to the next part, which is part G. It says, now assume the bed of the truck is frictionless, but there's a spring of constant 9,200 newtons per meter attaching the crate to the truck. So here we are. The truck is initially at rest and it accelerates 25 meters per second in 10 seconds. If the truck and the crate have the same acceleration, so now we know the acceleration is the same, derive an expression for the extension of the spring as the truck accelerates. Express your answer in terms of A and M, as well as any constants. And so some of the things that we could put in are time. We probably have Vx, we probably have Vox, and we would have K, and that would be our constant. So the first thing we need to do here is come up with an expression for the acceleration in the x direction. So our velocity is equal to the original velocity plus the acceleration times time. And so the acceleration is equal to our velocity minus our original velocity. So final, let's just put that in, all divided by time. We know that for this box, the sum of the forces should be equal to ma since it's accelerating. And the forces here are the force of the spring. So we know the force of the spring is equal to kx. Oops, put ka. That should be kx. That's the only force that we're worried about. That is the thing that is pulling that box this way. So this is kx, and that is equal to m times a. So now we want an expression for the extension of the spring, so that would be x is equal to m times a all over k. But remember, we said that a is actually equal to this, so now we're going to rewrite this again. This is x is equal to m times, m over k times v minus, or vf minus vo all over t. And so there is our expression. Point-wise, we'd probably look at, you need to have this one, this statement here. We'd have to have this equation, this one. We'd have to rearrange it and then substitute everything. So on this one, I think they're missing some things here. I really think that you probably don't need to have, well, you do need the M, you probably don't need the A, but you need the T, the VX, VOX, and K, or this could just be VF and VO. So any way you go, just make that change on your problem itself so you can kind of see that. Is there more to the problem? Let's take a look and see. It says using expression part G. For part H, it wants you to find the extension of the spring. So here we've got x is equal to 900, so that was the mass, divided by our k value, 9,200, times, now we've got our final minus our original velocity, all divided by the time, which was 10 seconds. And so here it is 0.24 meters, and that is the stretch of that spring. You would probably get 2 points for that, one for plugging everything in, and then one for your actual solution itself. For the next part, yes, there is a next part. It says, at some time later, the truck is moving at a constant speed of 25 and the crate is in equilibrium. A student determines that the extension of the spring is less than it was previously due to the fact that friction between the truck bed and the box is high, which prevents the box from pulling on the spring. They want to know what is correct about what the student says, and the thing that is correct about what they say is the spring extension. So here the spring extension is less, and the reason we know is the velocity is constant, so your acceleration here is equal to 0. So if your acceleration is equal to 0, there should be no stretch in that spring. What's wrong with what they said? They said it is frictionless. LESS. And they said, why is this incorrect? And it's because it says Um, at some time later, a student determines the extension, and so what we have to do is move back up to the directions, and we'll notice that at the very beginning of this problem it says the truck and the truck bed is frictionless. So it's actually in the problem itself. So when it says why, you just put in problem directions, and then it says assume frictionless. So kind of a goofy thing, but they'll do it to you. And that is the end of this problem.